Hello. So let's look at a second problem in introductory dynamics. So as I said, I'm collecting I think 40 or 50 problems that I think are important, and at the end I'm gonna collect them in a book, like in a workbook. And through these problems, I try to show how to approach dynamics problems. All right, in this problem, as you can see, we have at the instant shown, a camera in A is used to measure the velocity and acceleration of car B. So first off, let's read this statement again. What does it mean that we have a camera in car A that's used to measure the velocity and acceleration of car B? What type of acceleration and velocity this camera or the information of this camera is used to calculate? So because the camera is not fixed, it is essentially mounted in car A. So the measurement are in fact for car B with respect to car A. So right away you can say that the data is going to then to be converted to V velocity B with respect to A and velocity acceleration of B with respect to A. We have the radius of curvature of B, because B is essentially traveling on this curved path, and we are being asked to compute the registered velocity of registered velocity and acceleration by the camera of A. Again, it is what we are computing is the relative acceleration and relative velocity. Velocity of A is 40 meters per second, B is 30 meters per second, and look at there is no vector sign, so we essentially have the magnitude of velocities of both A and B. You have this angle as well. We need this because at the end of the day, if your goal is to have initial velocity and acceleration of B, you need to know how to go from relative velocity and acceleration to initial velocity and acceleration. So what we have here is the velocity of B increases by 2 meters per second square, and velocity of A remains constant. Velocity of A remains constant, and it's a straight line, pretty straightforward. Right away you could say what the acceleration of A is. Initial acceleration of A is equal to 0. The velocity of B increases by 2 meters per second square. In other words, the magnitude of this velocity increases by 2 meters per second squared. So you have to be very careful. B is traveling on this curved path. Velocity vector is always tangent to your path. So, and this velocity increases by 2 meters per second squared. The rate of increase is 2 meters per second. So let's look at the velocities first. We have two fundamental equations to compute accelerations of velocities. We know that initial velocity of B is initial velocity of A plus velocity of B with respect to A. And same thing for acceleration. So to compute velocity of B with respect to A, because that's what we're being asked to compute, because the camera, again, mounted in A, or the camera is being set up in A, and the data which is recorded by this camera is relative velocity and relative acceleration. So we know these are the quantities we are looking for, VB with respect to A and VAB with respect to A. Alright, so then you look at these two equations and say, alright, so if I know, so if you look at it backwards, let's say you have been given this problem and you have been given this problem to compute these quantities. You have already translated the problem into an understandable language. You know that you're looking for these two parameters. And you know that right away these two parameters, these two relative acceleration and velocities, appear in these two fundamental equations, which you have seen in last year physics high school and first year, second year physics in university. So you know that, all right, so once you write down these two equations, because these two equations contain the parameters you're looking for, you know that, or right away, you know that you know VA, and right away you know that you know AA, right? Because this was 0, this is known, and the axis, and VA is always along y-axis. So you are looking for VB and AB. Let's look at VB first. First off, VA is 40 E hat Y, and I'm using E hat to indicate the unit vector. So I'd like to compute everything in vectorial form. So this is the vector for velocity of A. And for velocity of B, I have minus 15 E hat X plus 15 the square root of 3 E hat Y. Where does this come from? You know that this is the velocity of B because it's always tangent to the curved path. And you know this angle 30. So all you need to do is you have this velocity and you need to decompose this velocity into its two components, right? And this is 30. You could already see where does this 15 comes from because it's 30 multiplying sine 30, which is 1 over 2. Okay, think about it and write it down. Decompose this velocity into its two components, and then you get where this comes from. A negative sign, obvious, because we assume that the positive vector, the positive x-axis, points to the right. This velocity already points to the left. So the x component would point in this direction, which is negative x. Same thing about E hat y. So we simply compute the component of this velocity along y-axis. And you know where this comes from because you know it comes from cosine 30. All right. Now we have the velocity of B, we'll have the velocity of A. We simply substitute these two in equation 1 and then we solve for VB with respect to A. That is what we're looking for. So you can do the simple math here, simple algebra, and then you find out that the velocity of B with respect to A is minus 15 E hat X and minus 14.0 E hat Y. And you could already see that. I mean, once you solve a problem in physics, the problem try to make sure that the problem makes sense. All right, if you think about it, if you think about this car, as you go with velocity of 40 meters per second, kind of this, you could physically, intuitively understand that because this 40 is larger than 30. So this velocity in y-axis is also smaller than 30. And you could see that with respect to A, if I was a passenger in car A, I could see that B would essentially go much slower. And to me, in fact, B goes backwards. It goes down. Because to me, because it goes faster, this is what I see. I see that this car, with respect to me, essentially I'm going this way, but the car stays back and it goes further back, right? So your answer mathematically and physically, also physically, should make sense. And this makes sense. And for the magnitude of this vector, we simply have a vector of x and y. You square both x and y components and add them together and compute the square root of that. This is pretty straightforward, so you can do it yourself. Let's look at acceleration. Again, we have this equation 2 unknown. In equation 2 is a sub b. And if we have a sub b, then we can easily compute this one we are looking for. But this is a little bit more involved to compute A sub B. So we know that the magnitude of this velocity is 30. We know that the B is traveling on this curved path. So one of the many ways you can compute is to look at this acceleration in tangential and normal frames, right? Once you look at this acceleration in tangential normal frame, it's pretty straightforward, right? Think about the acceleration in tangential frame. What is the acceleration in tangential frame? You simply have this 2 meters per second squared as your tangential acceleration, right? Because tangential acceleration is the one that dictates the change in your velocity. So, and then we have normal acceleration. Normal acceleration is simply the velocity squared over the curvature, the radius of curvature rho. And and the radius of curvature is given here, 200 meters. So we have velocity, we have the radius of curvature. We simply do this math, and then we find both components of acceleration. So if you look at this figure, this is your tangential component, this is your normal component, and all you need to do again to be able to do all your computations in your Cartesian frame is to project these two components into your Cartesian frame. And once you do that, again, you're going to use the cosine and sine 30, and this is pretty straightforward. I think you can see where each term comes from. For example, where does this component comes from? Negative 2 sine 30. 2 is your tangential acceleration component, and you're looking for e hat x component. So you multiply 2 by sine 30, this angle sine of 30, to compute this component of tangential acceleration. Right? So pretty straightforward. You can justify each component, and you're going to see that that's the total acceleration vector. Now that I have both accelerations, a sub A acceleration for car A and A sub B acceleration for car B, all I need to do is to just substitute them in equation 2, add them together or subtract them from each other to find A, B with respect to A. Once you do that, you'll find out that this is your total acceleration of B with respect to A. Again, back to the original question was that we set up this camera in our car A, and then we record the velocity and acceleration of car B, and that's what we're looking for. Because we want to know what do we get, because that's what happens, right, in practice. So we got the data in car A, and now we want to know how to interpret that data. So I have this acceleration of B with respect to A. To compute the magnitude, we simply, again, this is a vector. And if you were asked to compute theta, the angle of this vector with respect to, for example, horizontal axis, you simply compute a tan inverse of 0.518 over 4.897. Why? Think about it. I have the x component, and I have the y component, right? So y component, and I have the x component. So this angle, right, is the tan inverse of y component over x component. So that's why this angle is tan inverse of this quantity. So this is how we compute the angle. So to summarize, we had this camera set up in A. We recorded the data. Question is compute the what is this data? How can we interpret this data? We can interpret it as the velocity and relative velocity and acceleration of B with respect to A, and we use the information we are given to compute velocity and acceleration of B with respect to A. Email me with your questions. My email is available on About page. Also, you can communicate with me through LinkedIn. All right. Thanks for paying attention.